Good morning to all. I am Dr. Thayalan, retired professor, Madras Medical College, and we are planning to have series of lectures on radiation physics. I hope this may be useful to the undergraduate students of Allied Sciences undergoing BSc Radiology Imaging Technology, BSc Radiotherapy Technology, Diploma in Radiodiagnosis Technology, Diploma in Radiotherapy Technology. I hope this will also be beneficial to MSc Medical Physics students and students undergoing postgraduate courses in MD, Radiology and Radiotherapy, etc. So as a first lecture, we shall talk about some important concepts used in basic radiation physics. First, we address what is radiation. Radiation is small packet of energy. It travels as waves through space or matter. It transfers energy from one point to another. There are two types of radiation. One is photon radiation, which is nothing but X-rays and gamma rays. Other type of radiation is called particle radiation, which involves electron, proton, neutron and alpha rays. Mostly, the particle radiation has less penetrating power and it can be easily stopped by even a paper. Whereas photon radiation can travel for a longer distance and having higher penetrating power. It passes through few millimeter of metals. So radiation is further divided into ionizing radiation and non-ionizing radiation. In general, electromagnetic radiation is nothing but which possesses electric field and magnetic field and propagate in the space in the form of waves. The distance between the two constituent crusts is known as wavelength. It travels with the velocity of light. The various components of electromagnetic radiations are radio waves, microwave waves, infrared, visible light, ultraviolet, X-rays, gamma rays and cosmic rays. If you draw a line here, the right side of the spectrum consists of cosmic rays, X-rays, gamma rays and ultraviolet. They have lower wavelength and higher energy capable of ionizing the matter. In the left side, if you come across, you have radio waves, microwaves, infrared and visible light. They have lesser energy and higher wavelength. So in general, electromagnetic radiation has no mass. It is unaffected by electric and magnetic field. It travels with a constant speed of 3 into 10 power 8 meters per second. Whenever it travels in the medium, it gets absorbed and gets scattered. So in general, it is called attenuation. The radiation we use in medicine are X-rays, gamma rays, visible light and radio frequency. Radiation has duality. That means it has wave nature and particle nature. X and gamma rays, they travel like wave and interact like particles. Mostly, it is always interested to have interaction with the electrons and atoms, whose size is comparable with the wavelength. Mostly, the X and gamma rays wavelength is in nanometer. So, those matter having nanometer size as more probable for interaction. Electromagnetic radiation has property of wavelength, frequency, speed and energy. It is related with the equation C is equal to nu lambda. That is, the speed of electromagnetic radiation is equal to frequency into wavelength. Wavelength is measured in nanometer and 1 nanometer equal to 10 power minus 9 meter. Frequency is measured in hertz. 1 hertz equal to 1 cycles per second. Radiation also possesses particle characteristics and obey the equation E is equal to h. That means each photon energy is given by h nu. H nu can be reduced to hc by lambda, where h is equal to Planck constant, which is equal to 6.62 into 10 power minus 13 joules second. If you replace the value of h in this equation and the velocity of light in the place of c, then it can be reduced to 1.24 divided by lambda. That means energy of the photon is equal to 1.24 divided by lambda. If the lambda is expressed in nanometer, the energy is measured in kilo electron volt. In addition, Albert Einstein established an equation E is equal to mc square, where E is the energy, m is the mass and c is the velocity of light. If you destroy a mass of m, then equal amount of energy will be released in the matter. This is the basis for the model of atomic bomb, preparation of atomic bomb, and for which he was awarded the Nobel Prize in 1921. What is ionizing radiation? Ionization is nothing but removal of one or two electron from the neutral atom. That is, removing an electron from the atom is called ionization. X-rays, gamma rays, ultraviolet, alpha particle are capable of doing it. Hence, they are called ionizing radiation. They have sufficient energy to do ionization. As a result, what happened? Ionized atoms and molecules are produced, or ion pairs are produced in the matter. What is non-ionizing radiation? Visible light, infrared, ultraviolet, radio waves, DV broadcast having non-ionizing radiation. They have energy not sufficient to produce ionization, and removal of electron is impossible in this type of radiation. Therefore, the biological effect of non-ionizing radiation is very less or rare. Where from the radiation comes? The radiation comes from the atom of an element. What is the element consist of? The element consists of a nucleus in which proton and neutron is present. Outside the nucleus you have orbits. The orbits are called K, L, M and N. Each orbit having a subcell, the name of SBDF. Outside the nucleus you have electron. These electrons are revolving in circular and semicircular elliptical orbits. Each atom, each element described in terms of atomic number and mass number. Atomic number is the number of electrons or protons in the atom. It is designated by the letter Z. Mass number is the total number of protons and neutrons in the nucleus and designated by the number A. In general, element is described as A superscript, Z is the subscript and X is the element. An atom is said to be an isotope having the same atomic number with a different mass number. If the isotope performs radioactivity, it is called radioisotopes. Example, cobalt 59 and 60. The radioactivity takes place when the isotope is having high N/Z ratio. During radioactivity, it gets stabilized by performing alpha or beta decay. Every electron in an atom has binding energy. Binding energy is the amount of energy that must be supplied to remove an electron from an atom. Its magnitude depends on the nature of element and its cell. It is greater for high Z element and greater for K shell electron. Since it is the energy supplied, the binding energy is always negative. The binding energy is measured in electron volt, which is the unit of energy in atomic physics. For example, K shell hydrogen have binding energy of minus 13.5 electron volt, whereas K shell tungsten is a binding energy of 69,500 electron volt. The tungsten has higher binding energy because the atomic number of tungsten is higher than hydrogen. Electron volt. What is 1 electron volt? The photon energy is expressed in terms of electron volt. 1 electron volt is the kinetic energy imparted to an electron accelerated across a potential difference of 1 volt in vacuum. For example, if you take two terminals here and maintain one potential difference of 1 volt, if you want to move one electron from this end to this end, how much kinetic energy we have to give? That is called 1 electron volt. The electron volt is connected with the joule. 1 electron volt equal to 1.6 into 10 power minus 19 joules. In practice, kilo electron volt, million electron volt are used as a units. 1 kilo electron volt equal to 1000 electron volt. 1 million electron volt equal to 10 power 6 electron volt. This table shows some of the elements we come across in radiology and radiotherapy. and this shows the atomic number. The third column gives the binding energy of the K shell electron in kilo electron volt. For example, iodine atomic number is 53 and binding energy of the K shell is 33 kilo electron volt. Barium atomic number is 56 and K shell binding energy is 37 kilo electron volt. Tungsten, which is used as a target material in the X-ray tubes, 74 atomic number and the binding energy is around 70 kilo electron volt. Radiation obeys inverse square law. That means the radiation intensity is inversely proportional to the square of the distance. Intensity is proportional to 1 by d square. As the distance increases, the radiation intensity decreases. Suppose if you take 2 points, D1 point corresponding intensity is I1, D2 point corresponding intensity I2, the relation can be coined as follows. I1 by I2 is proportional to D2 square by D1 square. Double the distance means quarter the intensity value. If the distance increases from 1 to 2 meter, intensity reduces from 100 to 25 milliroentgen. You can see in the diagram. So this is the point where the intensity is 100 mR at 1 meter from the source. So if you go to 2 meter, the radiation intensity reduces to 25 mR value. As the distance is doubled, the radiation is become a quarter value. Radiation undergo attenuation because of absorption and scattering. The nature of attenuation is exponential in nature and follow the relation n is equal to mu into n into delta x, where n is the number of photons removed from the beam. Delta x is the thickness of the material. If you see the graph, attenuation graph, it shows exponential nature. That means initially it falls, it decreases very rapidly. After that, the decrease is very slow. So this can be given by a general equation. N is equal to n0 into e to the power of minus mu x. X is the thickness of the absorber or material. Mu is the linear attenuation coefficient. The negative sign indicates that it is decreases in nature. E is an exponential function and n0 is the original number of X-ray photons. N is the photons after the transmission through the absorber X. What is linear attenuation coefficient? Linear attenuation coefficient is a reduction in radiation intensity per unit path length and its unit is centimeter minus 1. The linear attenuation coefficient depends upon atomic number of the material, density and energy of the radiation and thickness of the absorber. The table below shows some of the material we are used in medicine and its density value and the electron density value as well as the linear attenuation coefficient for 50 kilo electron volt energy of the X-ray photons. You can see here compact phone which is having the highest density, having the highest linear attenuation coefficient compared to water or soft tissue. Radiation quality is described in half-value layer. What is half-value layer? It is the thickness of the material that attenuate the radiation beam by 50%. That means, suppose if you take the number of photon is 100, what thickness we need to reduce the 100 to 50 number in the path of the beam. So it depends upon the energy as well as the density, atomic number and medium density. The HVL is used to describe beam quality since the beam is heterogeneous in nature. HVL of soft tissue is 2.5 to 3 centimeter. HVL and linear attenuation coefficients are related as mu is equal to 0.693 divided by HVL. One can also reduce a useful quantity what is called mass attenuation coefficient, which is equal to mu by rho. It is expressed in centimeter square per gram. There is another important relationship is called 10th value layer. This is equal to 3.3 into HVT value. The 10th value layer is very useful in designing the shielding material for radiation insulation. Luminescence is another important property of radiation. The material absorbs energy from the external source and re-emit that light as light in the form of luminescence. The material which does luminescence are called phosphors. Actually, what is happening? Every medium has what is called valency band and conduction band. When the energy is given, the electron from the valency band go to the conduction band and later it returns to the valency band by emitting the excess energy in the form of luminescence. There are two types of luminescence. One is called fluorescence, the other one is called phosphorescence. Fluorescence is instantaneous emission, happens less than 10 power 8 seconds. Phosphorescence is the delayed light emission, happens greater than 10 power minus 8 seconds. The phosphor we use in radiology or medicine is sodium iodide, cadmium tungstate and zinc sulfate or cesium iodide. This concept is used in intensity screens which are used in cassettes in screen film radiography. In summary, radiation is a form of energy, comes from the atom. It has both wave and particle nature. Radiation can be classified as ionizing radiation and non-ionizing radiation. Ionizing radiation is capable of removing electron and produce biological effect. Radiation energy is measured in electron volt. Ionizing radiations are used in medicine. Example, X-rays and gamma rays. Radiation undergo exponential attenuation due to absorption scattering in the medium. Radiation obeys inverse square law. As the distance increases, radiation intensity decreases inversely. Radiation can also cause fluorescence. This property is made use of some phosphor material for medical applications. Thank you. We shall meet in the next lecture.